let's explain refraction using Huygens theory. So let's see how to draw the refracted wavefront using Huygens theory. See, that's the interface, that's the boundary which separates two medium from each other. This is medium A and this is medium B. Here the speed of light is v1, and in this medium the speed of light is v2. So let's say that light is moving from rarer to denser. Say this is the rarer medium, and for example this is denser medium. So here the speed of light will decrease. Say for example we say that v2 is v1 by 1. Say for example 2 this thing. So light will decrease by 1.2 times as compared to v1 there. Okay. Now there is a wavefront being incident. Okay. I'll draw the wavefront with the help of the red color here. So that's the incident wavefront. That's the incident wavefront. So AB is the incident wavefront such that this is point A, this is point B. Okay, so light rays are coming like this. So we have to draw the light rays. Let's draw the light ray with the blue color. So light rays definitely must be perpendicular. So that is very important to understand that this angle must be perpendicular. Okay, so this is how the light rays are coming. Okay, so that's the light rays coming. Now we have to draw the refracted wavefront. AB is incident wavefront. So AB is incident wavefront. Incident wavefront. We have to draw the refracted wavefront. It's quite simple. Say for example, light in time t from A is still traveling in this medium A. This medium A only. Okay, don't be confused with this A and A. So still light is traveling in this medium, and say in time t it has covered the distance v1t such that from A the light reaches A dash. Light reaches A dash there. That's the point A dash. Correct? And that's distance v1t there. Now from point B in the same time the light will now move to medium B, which is a denser medium, and how much distance it will travel will be 1.2 times the distance traveled by light in this medium in the same time interval. So if you will measure this, then that's coming out to be 9.5 centimeter. So 9.5 centimeter. So it will, here the distance traveled will be less by how many times? 1.2 times. So if we use a calculator and to calculate the distance, then it is 9.5 divided by 1.2, that's 7.9 centimeter. So we have to take the radius to be 7.9 centimeter from B and draw the circle, that is a sphere in 3D. So 7.9 is almost 8. Let's take it. Yeah. So from B light will be traveling this distance, that is V2t. V2t there. V2t there. Okay, so in this medium there. Let's take another point C. Somewhere on the wavefront, from C first light will reach the surface. So the light ray is coming, that must be perpendicular, that I told you already. Now this distance, if you see, is 5 centimeter, and this was 9.5 centimeter. So what is the left out distance is 4.5 centimeter in this medium, और उसका corresponding distance इस medium में क्या होगा? उतने टाइम में जितने में उसको यहाँ पे 4.5 सेंटीमीटर कवर करना है, उतने ही टाइम में वो इस मीडियम में कितना कवर करेगी? 1.2 टाइम्स लेस. So 4.5 by 1.2 will come out to be 3.75. So let's take the radius to be 3.75 and draw the circle from this point there in medium B, 3.75. So that's 3.75. So from here 3.75, let's draw the circle there. So after time t, light from A will be somewhere on this interface at A dash, from B somewhere on this circle, and from C somewhere on this circle. Now from A dash we will draw the tangent, the envelope to all these circles, and it will automatically come exactly the tangent. You see, it's exactly coming the tangent as we have drawn these angles to be perfect normal. So this, that's B dash. So A dash B dash is the refracted wavefront. A dash B dash is refracted wavefront there. And how the incident light rays are going? The incident light rays are going, just drawing with the blue only there. So the incident light ray is going like this. Okay, that's a refracted light ray. That's the incident light ray. That's refracted light ray. If you draw the normal, then the Snell's law should also hold good. So if you draw the normal here, then you know that in this diagram, what is the angle of incidence which the light ray makes with the normal, the incident ray, that's I. This is a refracted ray, that's angle of refraction, and you already know that this is I, then this wavefront will also, incident wavefront will also make angle I there. This is R, this is 90 minus R, this will be again R because this is 90 degree there. So wavefront surface से वही angle बनाता है जो corresponding angle of incidence या angle of refraction या reflection होता है. Now in these two triangles, you see in the first triangle ऊपर वाले में sin I निकालें, sin I, then sin I is perpendicular, that is V1t by hypotenuse A dash B, and in this triangle if you find out sin R will be perpendicular, this is V2t, you know, that's V2t. Okay, so that's V2t by hypotenuse A dash B, get cancel out, t get cancel out, अगर divide करें तो sin I by sin R will must simply coming out to be V1 by V2, which is nothing but the Snell's law, that which says that for a given pair of media, the sin I by sin R must be in the ratio of the speed of light in the two respective mediums there.